Hello. In this video, I'll be talking to you about rotating magnetic fields. Now, before I move on to rotating magnetic fields, there are a couple of things that I want to discuss first. First thing is I want to tell you about three-phase currents. Now, three-phase currents are typically three currents which are equal in magnitude and they're separated in phase by 120 degrees, like the one which is shown in this figure over here. And another thing I want to tell you is about something called as electrical degrees and something which is called as mechanical degrees. Now, these are not the exact definitions of electrical degrees or mechanical degrees, whatever I'm going to tell you right now, but however, just for simplicity's sake, let's define it like this for this particular chapter. So, electrical degrees is nothing but the phase difference between the two currents, or between two consecutive currents. Now here we have IA, IB and IC. The phase difference between each of them is 120 degrees. So in this case, the electrical degrees would be 120 degrees. And mechanical degrees is basically the mechanical displacement between two consecutive windings of your stator. And these two are related to each other using the equation theta E is equal to P by 2 times theta M. Again, whatever I have defined right now is not the exact definition. I have only tried to make things simple in this particular video for this particular chapter. Now moving forward, if we have a two-pole machine, for a two-pole machine, your theta E would be equal to 2 by 2 times theta M. And I forgot to mention, your P represents the number of poles. So therefore, your theta E is equal to theta M. Now we know that the theta E is 120 degrees in this case. So therefore, your theta M would be 120 degrees. So if I were to draw a two-pole stator, it would look something like this. You have your A phase, which is over here. This is your A dash and this is your A. And now remember, we found out that your mechanical degrees is 120 degrees. So therefore, your B would be 120 degrees away from your A. So this is where your B would be. And your C would be 120 degrees away from your B. So I'm sorry about this. Let me redraw it. So this would be where your C should be, and your B dash would be diagonally opposite to your B, and your C dash would be diagonally opposite to your C. Alright, so now moving forward, this is how the stator diagram looks like for a two-pole machine. Now this is your front view, but now if I were to draw an isometric view, this is how it would look like. So this is your A dash, this is your A dash, and you have current moving like this. If it is positive, I'll get back to this in a bit. All right, and let me redraw this again. I'll get back to what I was talking about over here in a bit. So this is your A dash, A dash, and this is your B over here, which looks something like this, and this is your B dash, which comes out from here, and this would be how your C would look like. I'm sorry, please forgive me for the drawing. This is A dash, and this is how your C would look like. And this is your C dash over here, and this is your B, and here is your B dash. All right, this is how the stator would look like from the side. Now, to understand how rotating magnetic fields work, I would request you to please pay your attention to this waveform up here. Now, at this instant of time, you see that your current is positive, your A current, the IA is positive, and your currents IB and IC are negative. Okay, and what it means to have a positive current is that basically if this is your A winding, what it means to have a positive current is that your current enters through A and it exits from your A dash. So therefore, as I have a positive current at A, I would find a current entering from A and exiting from A dash. Similarly, I have a negative current. So what it means to have a negative current is exactly the opposite. What it means is that I would have a current entering at A dash and exiting from A. So similarly, you see your B and C both are negative. So therefore, I will have a current entering from B dash and exiting from B, and similarly I'll have a current entering from C dash and exiting from C. Now, according to the right hand corkscrew rule, the magnetic field generated over here would be going in this direction, and similarly from the right hand corkscrew rule we find that our magnetic field in this case would be going in over here. So hence the resultant magnetic field or the resultant magnetic field vector would be in this direction, and we all know from a magnet that the fields go from the north to south. Therefore your north pole would be here and your south pole is over here. So now moving forward, if I were to look at the magnetic field at this instant of time, this is how would the resultant magnetic vector look like. Let me redraw this. So here we have B dash, A, C dash, B, A dash and C. Okay, so at this instant of time, as I pointed out over here, you find that your IB is positive and your IA and IC are negative. So in this case, what's going to happen, you have IA is negative, so therefore you have current entering from here and you have current exiting from here. Similarly, your IB is positive, so you have current entering from B, exiting from B dash, and your IC is also negative, so therefore you have current entering from here and you have current exiting from here. Now if you were to look at the field, so by right hand corkscrew rule we find that you have a field going out in this direction and you also have another field which is around this going in this direction. Similarly, you have a field which is going in this direction over here, and you also have another field which is going in this direction over here. I'm sorry, this is in the opposite direction actually. over here. This is in the opposite as per your right hand corkscrew rule. So you find that you have a field which is going out in this direction, and you have a field which is coming in this direction. So you have your north pole which is up here, and this is your south pole over here. So as you can see that the resultant field vector has rotated a bit. Now if you keep going forward and investigating through this graph over here, you'll find that the resultant field vector is rotating. Now a question might be raised: what happens if we have two windings per phase? In this particular scenario that I've explained, we have only one winding per phase. So what would happen if we have two windings per phase? What I'm trying to say is that here you have just A, B and C. But what if you had two windings, like you had an A1 and an A2, a B1 and a B2, and a C1 and a C2? What would happen then? So let me just redraw this figure and let's see how would your stator look like. So what I'm going to do is I'm just going to draw this one first. You have A. I'm just copying the same arrangement that we have seen over here. So you have A, C dash. So you have, and let me put this as A1. You have C1 dash. Then you have B1. You have A1 dash. Then you have C1, and you have B1 dash. And now for the next side of the stator, I will be writing the very same configuration, the very same arrangement on the other half of the stator, but only instead of 1, I'll be replacing that with a 2. So what I'm trying to get to is, here I will have an A2, and then I will have a C2 dash over here. Then following this, I will have a B2 over here, and then I will have an A2 dash, and then I will have a C2 over here, and I will have a B2 dash over here. So now how would the magnetic field look like when we have two windings per phase? So just to give you a clear picture, let's go to a fresh page. So I've redrawn it over here, and let's see how the magnetic fields look like in this case. So if we were to look at how the magnetic field looks like at this instant of time, as denoted by the black spot over there, this is what would happen. So we see that your current A is positive and your current B and C are negative. Now when we have two windings per phase, the current which enters your A1, the same current would be entering A2. So from the sign convention seen previously, for positive, we see that the current enters from your A1 and it exits from your A1 dash. So what is going to happen is, we'll have the current entering from A1 and you'll have the current exiting from A1 dash. And since I've mentioned that whatever current is introduced to A1, the same current would be introduced to A2. So we have a positive current which is introduced to A2. We would obviously expect a current which is, and we would expect the current to enter A2 and it would exit from A2 dash. Now in this case, your B and C are negative. So therefore your current would be entering from B1 dash and it would be exiting from B1, and it would be again entering from B2 dash and it would be exiting from B2. Similarly, your current would be entering from C2 dash and exiting from C2. again your current would be entering from C1 dash, which is over here, and exiting from C1. Right? Now if we look at the magnetic field over here, by right hand corkscrew rule, we'll find that the magnetic field around here would go in this direction, and also the magnetic field around here would be going in this direction, correct? And the magnetic field which is over here would be going in this direction. Sorry, I think the arrow is not very clear. Let me do this. Let me draw it with another color. This is your C1 dash, and that is your B1. So therefore it goes in like this, and this is your B1, right? So you have another arrow going in this direction. So this is the direction of your magnetic field. At the same time, by the right hand corkscrew rule, you'll have an arrow in this direction, and you'll have another arrow going in this direction. So therefore, oh wait, there's one more thing that we need to look at, that is this one. So again, by the right hand corkscrew rule, you have an arrow going like this, and you have another arrow going in from here. So as you can see, you have two norths and two souths. This is your south pole over here, and this is your other south pole over here. This is the north pole over here, and this is another north pole over here. So what you have is a 4-pole motor now. So basically, when you increase your windings, the number of windings per phase, your number of poles increases. Now previously we saw the relationship that theta E is equal to P by 2 times theta M. Now we know that theta is equal to 120 degrees, the number of poles is 4, and this is theta M. So you do the math, you get theta M is equal to 60 degrees. So what does this indicate? It indicates that the mechanical displacement between any two consecutive windings would be 60 degrees. So therefore, let's see, in this particular case, again let me use a different diagram. So in this case, we have your A1 which is over here, and you have your B1 which is over here. So this is approximately 60 degrees. Again, I have not drawn the diagram with perfection, but this is approximately 60. So now let's see how the field rotates. Okay, let me just erase this real quick and get back to the previous color that we were using. This is north, north, south, south. So what we have over here is basically a quadrupole. You have a north pole going to a south, this is what we have. You have a quadrupole over here. Now if I were to look at how the resultant magnetic field were to look like at this particular instant of time, let's investigate that right now. So at this particular point of time, you'll find that your current A is negative and your B and C are positive. So moving on those lines, as